Hey, in this tutorial we're looking at section 11.6, which is talking about the logistic equation. So in this logistic growth, can be written as dn dt equals c times n outside of p take n, or dn dt equals kn outside of 1 minus n on p. Okay, k is our growth rate. Okay, p is the carrying capacity. Okay, that's our maximum value, like we've had in our bounded growth. Okay, n naught is our initial value. Okay, and if k is bigger than 0 and p is bigger than n naught, which is bigger than 0, then we get n of t equals p times n naught on n naught plus p minus n naught e to the negative kt, which is also equal to p over 1 plus p on n naught minus 1 times e to the negative kt. Okay, graphs of our logistic growth look like this. Okay, and we have a point, and we talk about this a little bit more in a second. Okay, where it's p on 2. Okay, that's our maximum rate of change of growth. Okay, we also have three unknowns in this, which is p, n naught, and k, and so we need three conditions to find their values using simultaneous equations. Okay. Some you might know without the need of simultaneous equations. Often n naught you may not need to. Okay, but then you'll probably need it for p and k. Okay, at the point where t equals 1 on k log to the base e of p on n naught minus 1, okay, then we find that n equals p on 2. Okay, so this point, okay, that we're just talking about corresponds to the point where the second derivative equals 0. So therefore, this point represents a non-stationary point of inflection and is a point of maximum rate of growth, as we were talking about just a minute ago. Okay, so we've got a couple of worked examples to do. Now, the worked examples are quite long in this section, so hopefully I can I've got enough space to do all the working out. Okay, but if not, I'll just have to skip a couple of steps. So for worked example 12, a rumour is spreading in a neighbourhood that contains 800 people. Okay, so we know we've got 800 people. Okay, the rumour spreads at a rate proportional to the product of the number who have heard the rumour and the number who have not yet heard the rumour. At first, only 2 people in the area have heard the rumour, but after 4 days, 15% of residents in the neighbourhood have heard it. Okay, so in part A, we need to let n equal n of t. Okay, be the number of people who have heard the rumour after t days. Write and solve the differential equation. Okay, so the maximum number of people, okay, is p equals 800. Okay, we know then that our dn dt, okay, well that's going to be k times n outside of, well, our p was 800, so we're going to say 800 minus n. Okay, and we also know n naught equals 2. Okay, so what we're going to do is we're going to invert this and integrate it. Okay, so we're going to say then that t equals the integral, okay, of 1 over kn, so that 800 minus n dn. Okay, now we can bring out our 1 on k as a factor, okay, and then we can multiply by k, so we can say that we actually get our kt instead. And when we integrate this, okay, now it's a little bit of a pain because we have to use our partial fractions. So I'm just going to skip over our partial fractions part here, okay, because what we can say that it is that our kt equals 1 on 800 times the integral of 1 over n plus 1 over 800 minus n dn. Okay, so hopefully we're all pretty familiar by this stage of how our partial fractions work. Okay, so it does step out our partial fractions pretty well there. Okay, so if you're having any trouble with that, just make sure you have a look at that part. Okay, so what we're going to do is we're going to multiply by our 800 though, to say we've got 800 kt. Okay, and that's going to be, when we integrate this, we're going to get log to the base e of the modulus of n minus log to the base e of the modulus of 800 minus n plus c. Okay, now we don't really need to worry about our modular signs because we know that n is between 2 people, the amount of people that started with, and max of 800 people in the population. So we know n can't be a negative value. Okay, so we also are going to use this information now. Okay, so we're going to say let t equal 0 and n equal 2. That way we're going to be able to find our c, because when t equals 0, our 800k t all equals 0. Okay, so we're going to get 0 equals log to the base e of 2 minus log to the base e of 800 minus 2 is 798 plus c. Okay, when we rearrange that, we find that we can end up with the value for c of log to the base e of 399. Okay, using some log laws there. Okay, so that means now that we get 800 kt being equal to log to the base e of n minus log to the base e of 800 minus n plus log to the base e of 399. Now using our log laws for that means that we can say that our 800 kt is equal to log to the base e of our 399 n over 800 minus n. Hey, so we're getting there. We can also say we know that when t equals 4, that we had 15% of our population now knew about it. Okay, so 15% of our 800 gives us an n value of 120. Okay, so we're doing this so we can find our k value. Okay, because basically we're going to have 3,200k equaling log to the base e of 399 times 120 over 800 minus 120. Okay, and when we do that, okay, that means that we get a k value, okay, of 1 on 3,200 log to the base e, okay, of 1,197 over 17. That's just what we can simplify this to. Okay, which means that our k value has an approximate value of 0.001329. Okay, so that also means, okay, that our 800k, so I'm going to have to come up here now, our 800k is going to equal 1.0636. Okay, so that just means now that what we can do is we can rearrange our equation that we had here. Okay, we can do our loopy method, so we can go e to the power of 800 kt equals this side here. Okay, and we know what our k value is. Okay, but what we're going to do is just going to leave that k value out. Oh no, we don't need to leave that k value out. It's not too bad. Okay, so what we get is we have our 399n over our 800 minus n, okay, equals e to the 800 kt. Okay, so it just left out at the moment. Okay, when we run through, okay, what that means when we keep rearranging, okay, until we get n, then we get n equals, sorry, that should be n of t, okay, equals 800 over 1 plus 399 e to the negative 1.0636t. Now, of course, we could have actually come back here, okay, and look to see what we had here, so we knew how we could have set it up. Okay, so we could have set up with all of this information there because we knew what p was, we knew what n naught was. Okay, so it would have only been this k value that we would need to work out. Okay, so I've just gone through the longer way of actually going through using our differential equation stuff, but we could have actually skipped through all of this to use our actual form of our equation that we knew. Okay, so don't forget that we can do that. Just want to show you the full working out of how to derive it, but on an exam, I mean, you're not going to have room to do all this, so you could simply do one of our equations. Okay, so that is our first part for this worked example. The next part, part B, is determine the number of residents in the neighbourhood who have heard the rumour after 5 more days. Okay, 5 more days, okay, that means that T is going to equal 9 because we've already had 4 days. Okay, so all we're doing is simply subbing in T equals 9 into here, so that means that N of 9, okay, is just going to simply equal 778.3767. Okay, so we can say that 778 people have heard. Okay, for part C, okay, we've got after how many days have 50% of the residents in the area heard the rumour? Okay, so determine T when 50% of our 800 heard the rumour, so that's where we actually saying that N equals 400. Okay, now that's also though when we're at our halfway mark, when we're talking about P on 2. Okay, when N equals P on 2, our T equals this value here, so we could also do that. Okay, we could also sub our values into there. Okay, but what we'll do is we'll do it as they do it in the textbook and say, well, we get our N needs to be 400. Okay, so say our 400 equals 800 over 1 plus our 399 e to the negative 1.0636t. Okay, and we're rearranging that for t, so we'd have to do a bit of work here, multiplying through and whatnot. Okay, so when we do that, we find that we get a t value of 5.63. Okay, so we could just solve this in our calculator. We wouldn't need to go through and rearrange it by hand. Okay. So the last part is part D, which is sketch the graph. Okay, well, we know that we are pretty much everyone by the time we get to 9 days, so we won't worry about going past 9. Okay, and our P is a value of 800. So that becomes our asymptote here. Okay, and we start off with only 2 people knowing, so we'd only be slightly above our origin there, and we'd say we'd be going up to 9. Okay, so we come along. And up, something like that. Okay, and this is going to be your T for your time and N for your number of people. Okay, so we'll move on to worked example 14. Okay, so we're saying that in this one, a logistic equation has the solution y of x equals 200 over 1 plus 99 e to the negative x on 2. Using differentiation, show that the solution satisfies the equation dy dx equals y outside of 200 minus y over 400. Okay, so that's what we need to show for part A. So what we need to do, okay, is rewrite our equation here and say, well, we've got y equals our 200 outside of our 1 plus 99 e to the negative x on 2 to the power of negative 1. Okay, so using our chain rule for this, because we're a function within a function, we're going to be 200 times by our minus 1. Okay, times by our derivative of what's in here, which is going to be negative a half times 99 e to the negative x on 2. Okay, and that's all going to be times by what we had in our brackets, which is 1 plus 99 e to the negative x on 2, okay, to the power of negative 2. Okay, and we can simplify that down to, when say we've got 100, because we're going to be doing some cancelling out there, times our 99 e to the negative x on 2 over 1 plus our 99 e to the negative x on 2 squared. Okay, and that can simplify further. Okay, down to, okay, so I'm just going to see where we can simplify down to? Oh yeah, sorry, we've got a fair bit of simplification to do before we get to here, so sorry, I won't skip through that. Okay, so we can then say that we get 200, okay, over 1 plus our 99e to the negative x, x on 2. Okay, well, we know that's equal to our y, okay, that we had before. Okay, so we can do a bit of work here, okay, and say that we've got our 1 over 1 plus 99e to the negative x on 2, okay, is equal to y on 200, okay, dividing by 200. Okay, we can invert this to say we've got 1 plus 99e to the negative x on 2 equals 200 on y. Okay, so that means that we get 99e to the negative x on 2 equals 200 y minus 1. Okay, so that means that we can go the same denominators and say that we've got 99e to the negative x on 2 equals 200 minus y on y by making this y over y and subtracting them. Okay, so we're getting there, so we can say our dy dx that we had up here, okay, we can substitute what we've got here, okay, into our derivative, okay, because we know that our 99e to the negative x squared is equal to this. Okay, so we need to substitute that back in there. Okay, so it means that our dy dx, sorry, I'm just running out a little bit of room here. So our dy dx now, well, we'll go 100, okay, times by, as I said, we know this value is equal to this, so we can put that in, 200 minus y on y, over our 1 plus 99e to the negative x on 2 squared. Okay, so we can simplify that. That cancels straight down to be our y outside of our 200 minus y. Okay. Oh, sorry, I forgot one part. Sorry. Need to put in another step there. So we can also, of course, sub it into the bottom here. So we can say that that's 100 times our 200 minus y on y over 1 plus 200 minus y on y all squared. Okay, and that simplifies down to be our y outside of our 200 minus y on 400. Okay, if we were to multiply that out, okay, then we would end up with that. So we would again make this y over y, okay, bring them together as our fractions. Our y on the top, okay, it's going to cancel out. Okay, just leave us with 200 on y. Okay, and then we can square it and flip and multiply and such, and we're going to cancel out y's until we get our answer here. Okay, for part B, so that's just part A. For part B, we want to show that, I might switch colours here, make it a little bit easier. So start down here. We need to show that d squared y on dx squared, okay, is equal to y outside of 100 minus y, 200 minus y, all over 80,000. So for this, we're going to be doing our derivatives here. So what we do is we can actually do a bit of our knowledge of our derivatives here. So really, what we're doing is we're going to take our derivative of this. Okay, so when we do that, our d squared y on dx squared. Okay, what I'd be doing if I was taking the derivative of this is I'd be multiplying that out. Okay, so before I get to that, sorry, we should just say our dy dx is going to be equal to 200 y minus y squared, and that's all over 400. Okay, I'd split that up, okay, and say that we've got y on 2, take y squared on 400. Okay, so when we take our derivative for this, I'd say our d squared y on dx squared, right, well, we would simply be doing, reduce our power by 1, it's going to give us a half, minus, bring our 2 down, going to cancel, and we're going to get y on 200. Okay, but you can see that is vastly different to what they actually want it in our form. Okay, so we can't actually do it that way. Okay, so you can see they go through a bit of a process here, okay, on what we've got. Okay, so what they do is they actually go through and use our definition of our second derivative, being the derivative of the first. Okay, and so they go through doing that. It's a little bit of a weird process what they do there, really. Okay, to end up getting in the right form. Okay, because as I said, second derivatives really shouldn't be that complicated. Okay, but they do go through that little bit of a complicated process. Okay, of breaking up what our second derivative is. Okay, and subbing in what we know. Okay, and then taking derivatives of it, and so forth. Okay, so what we'll do is we'll keep moving on to part C. Okay, well, I'm not going to write out everything that there is for part B because you can follow it through. It's generally not too bad following it through. It's just a little bit of a different process. Okay, and I would completely understand, okay, if you're looking at that and going, why would you not just do what we've done up here? Okay, part C is hence determine the coordinates of the point of inflection. Okay, so what they do is we've got to say, well, our point of inflection occurs when our second derivative equals 0. Okay, so again, we'll see if we can use our form here and see if we get the same answer. I'm not sure if we will or not. Okay, so we'd be saying that we get 0 is equal to a half minus y on 200. Okay, so that means then when we rearrange this, we're going to get, well, minus a half equals our minus y on 200. Okay, which means we're going to get y equals 100. Okay, which is what they do get. Okay, they do get our y value as 100. Okay, so we need to substitute that back in our equation, okay, to actually get our x value. Okay, so the equation that we use is this one here. Okay, so we need it. We've got our y value. We need our x value. Okay, so we go, well, 200 over 1 plus 99 e to the negative x on 2, sorry, is equal to 100. Okay, when we rearrange that, well, we can divide by our numbers here, and so we can say that we've got 1 plus our 99 e to the negative x squared, okay, is equal to 2. Okay, we can take our 1 away and say we've got 99 e to the negative x on 2 is equal to 1. Okay, so we can then say, I'll come over here for this, e to the negative x on 2 is equal to 1 on 99. Okay, so we can say then that our, so they do a bit of an odd step here. They say our e to the negative x on 2 is equal to, oh no, sorry, it's not a weird step, I'm just looking at it stupidly. Of course we can invert this and say e to the positive x on 2 equals 99, sorry, ignore what I was going to say there. So our x on 2 equals log to the base e of 99, so x equals 2 log to the base e of 99. Okay, so that means that when we have our second derivative equals 0, or our point of inflection, okay, we can say that that's at the point 2 log to the base e of 99, okay, and 100. Okay, is what we can say here. Okay, for part D, it's a sketch graph of y versus x. Okay, and when you do this, you probably could have realised that we could have done some of these parts a little bit differently, which I'll talk about in just a second. Okay, so we start out at the maximum of our 200, okay, and we come up here. Okay, with our maximum there, we've got our y and we've got our x. Okay, and we know that partway between, that our 2 log to the base e of 99, we're at 100. Okay. So I think if we had a look at our equation, we'd probably be able to find out a little bit of the information here. Okay, and I haven't actually gone through that, I've just thought it out then myself, but I think if we had a look back at our equations here, okay, and did a bit of a comparison with what we got, okay, that we should actually be able to work out, okay, some of the information here. Okay, so we know that our P n naught has to equal our 200 up there. Okay, we need to be thinking if the bottom one becomes a little bit more tricky. We need to think P minus n naught then is going to equal, okay, our 99, and n naught there is going to be 1. Okay, so then we can work through and work out what that p value needs to be, etc. Okay, so that's all there is to this section. Okay, again, it's similar to sections that we've done in the past. We're just introducing new ways of using our differential equations.